So I'll get started. Okay, I should mute myself. There we go, because I can hear myself through the live stream. Yes, so my name is Jesse Velay-Vitow. I'm a PhD student here at the University of Toronto. I work on ice and ocean physics with the Pelche group. And this is the Canadian Meteorological and Oceanographic Society's student lecture. I'm going to be talking about an overview of the ocean, of the history, the present, and the future of investigating the oceans. There we go. So a bit of an outline of the talk. The oceans have proven a fascinating subject for generations of scientists, and indeed that interest extends pretty much as far back as people have been asking questions about the world. We know that all life came from water, and perhaps that's one of the reasons why we've always been drawn to understanding the ocean. There's a similar draw between mankind and the moon. Gentler than the life-giving sun, it has been accorded a mysterious air, often symbolically tied to fertility, insanity, trickery, and love. The tides combine these two powerful mythological entities in our history, and thus understanding how they interact has captured the minds and occasionally the obsessions of scientists throughout the history. A brief note, a lot of the information that I'm using for this talk comes from Tides, A Scientific History by David Edgar Cartwright, who was the director of the Liverpool Tidal Institute. It's a wonderful book, and I recommend it to everyone to check out. So the outline, I'm going to talk a little bit about the ancient past with questions asked by the Polynesians, the Greeks, and the Arabian world about the tides. Then I'm going to move to the not-so-recent and then the recent past, going over Newton, Galileo, Darwin, Dudson, and the Liverpool Tidal Institute. In the present, I'm going to talk about the advancements in satellite technology, high-performance computing, and give an overview of the work that I've done on the glacial oceans. And then for the future, it's kind of an open-ended thing. I have a lot of little subjects that ocean investigation plays into, and I'm going to talk about those and where those are going briefly. So without further ado, this was largely an excuse to use the DVD art for Moana, which is, as I understand it, quite an accurate depiction of Polynesian wayfinding. For thousands of years, these techniques, such as using the birds, the stars, the swell of the waves, allowed Polynesian navigators to find nearby islands and conduct journeys to them. The way that they developed these techniques was they had settled certain chains of islands in such as like the Marshall Islands, the Solomon Islands, and they had observed how nearby islands affected the tides on the coasts. And using this information, they were able to predict where other islands would be. And these were so effective that eventually they ended up inhabiting all of the islands that could sustain life in the Polynesian Triangle. These traditional techniques are actually still taught today, hence how we knew how to make them accurate for the movie that Disney put out. Moving more to Greece, Greek sailors, early Greek sailors, including the Phoenicians, Carthaginians, early Minoans, and Mycenaeans, developed many different navigation techniques. One of the most interesting ones, I think, is that they would take a line and wrap the bottom of it in tallow and drop it down to the ocean as a sounding line to figure out how deep the ocean was at that point, and use a rough constant slope formula to figure out how far they were from the shore. More interesting is that the most expert people at this were able to look at the sediment that was pulled up, stuck in the tallow, and use that as information. So really these are kind of the precursors to sediment cores that end up being drawn in the 20th century. They also used complex calendars, and this is why I have a picture of the Antikythera mechanism. If you don't know the history of this, it completely surprised scientists when it was pulled up from a wreck, because it was much more complex than any other artifact that they had yet seen. After investigating it with a bunch of techniques such as X-rays and whatnot, they figured out that it was actually a very complex calendar for keeping track of the stars, the sun, the moon, and even the Olympic Games. So you can see at this early date that there's some understanding that the moon is playing a role in human civilization and in the affairs of man. The last point is that a man named Pytheas journeyed all the way to the British Isles. He's the first person known to record the midnight sun. And he's also the first person to suggest that it was the moon that caused the tides. So even at that early date, oh, I'm just realizing I spelled Greece wrong. Oops. Yes, so he's kind of the first person to suggest this hypothesis. Moving towards the Arabian cultures, they had a long history of tidal knowledge. One of the ways that we know this is that later sources, such as Posidonius of Rhodes, cite works which are no longer extant. One of these is Seleucus, which Posidonius cited when he quite accurately described the tides at Gades. And we know that there's a long history before the first extant work, which is the work of Albumisar in the 9th century, because it's so developed at that point that it's very unlikely that this one person, just from nothing, was able to get that far and that deep. So there's a long history of investigation here. These records go on to be cited by Darwin when he's developing his tidal system of notation later on, which I'll get to in the 19th century. So out of the ancient past, we can now go to the not-so-recent past. Galileo noted that if what Copernicus said was true, and the Earth not only rotated on its own axis, but moved around the sun, then the tides would be a product of both the rotation of the Earth and the Earth's movement around the sun. He was convinced that this is, in fact, the case. And he wanted to set out and test that. Another person of note is John Wallis, who was a professor of geometry at Oxford. He was able to re-involve the moon in this by pointing out correctly that if what Copernicus said was true and the Earth moved around the sun, the moon was also moving around the sun, and it was actually, in fact, the Earth-Moon system that would be moving around the sun. So he brings the moon back into this, and this will be a theme throughout the talk, but his attempts to figure out the period of that effect did not match with the observed effect, which is because the tides are a complicated system and it cannot be simplified down to just one component. Another person to mention is Rene Dakar. He obviously had his fingers in everything at this point. He proposed a vorticity theory. His idea was that the swirling of the sun caused vortexes to move through the ether and then hit the Earth, which caused the swirling of the tides. This doesn't involve gravity whatsoever, and since it depends on something that doesn't exist, namely the luminiferous ether to be there, this theory ends up, it persists actually past the point of Laplace, but it's not correct. We can now talk about Newton, and one of the things is that in this period from the 17th to 19th century, we saw a large increase in empirical studies of the tides. People were taking long series of measurements at places like Brest in the United Kingdom and along the coast in the Netherlands and Belgium, mainly for the purpose of being able to accurately figure out when it would be safe to send shipping vessels and also fishing vessels and things like that. But increasingly now scientists were asking them to take these measurements and prescribing what level of accuracy they wanted to see. Newton's work in the Principia is largely correct. He offers up the effect of the sun on the moon's orbit as an explanation for the lunar fortnightly tide, which is he's the first to do that. And one of the specific long series that's asked for is Pierre-Simon Laplace, Marquis de Laplace, asks for a long series to be taken so that he can start to pull apart the lunar and the solar effects on the tide. I'll get to that in the next slide. Another important thing that happens at this time is the Academic Prize of 1740 is offered up for an essay on the ebb and the flow of the sea, or La Flux et Reflux de la Mer, by the French Royal Academy of the Sciences. The prize ends up being shared 4 ways by 3 people who you probably all know: Daniel Bernoulli, Leonard Euler, and Colin Maclaurin. The 4th man is Antoine Cavalieri, who was a Jesuit priest. 3 of them made important additions to the theory up until that point. Maclaurin is actually the first person to appreciate the Coriolis force, which, as we know in science, the first person to discover something is never the person it's named after. Euler shows that it's actually the horizontal component of the force of gravity, not the vertical one, that matters, which has to do with the way that the tide is stretched and pulled by the moon. And Bernoulli is able to actually predict high tides with a level of accuracy before that not seen in areas where those tides are largely dominated by the diurnal components. Cavalieri, on the other hand, argues for the now discredited vortex theory of Dakar, and so he did not end up having an impact on the future of tidal analysis. So now we get to the first person to actually try and put this all down into a cohesive theory. It had been realized for a long time that there were clearly semi-diurnal and diurnal, or semi-daily and daily contributions to the tides by various records kept in different locations. This has to do with the way the coastline is shaped. In some places, the semi-diurnal effect is reduced, and you can see a once daily high tide. Now, Laplace wanted as long a series as he could get to be able to pull these apart. And so his upper bound of what he wanted, or rather his lower bound, is he wanted 18.6 years, which you'll recognize as the synodic period of the moon, or the time that the moon takes to fully rotate around the line drawn between the Earth and the Sun. Now, he wasn't able to quite get this because at this point, without computers or cameras, taking a series of measurements was just a dude who went out twice a day and kind of eyeballed when the tide was hitting its high point and its low point, and used a measuring stick to figure out where those were. So there's a lot of noise and observational error, especially when it's foggy out or when it's raining. These people it's quite interesting. There's some of these people who are so dedicated. Like, I think there's one guy who spent 20 years every day going out and taking these measurements. Like, that level of dedication is amazing. And now we just can use cameras, so it's a bit simpler. So Laplace had to settle with 15 years, and he publishes his treaty, or La Traité de la Mécanique Céleste, in 1776. And he's the first to lay out a real theory of the tides referencing the sun, the moon, and the rotating reference frame of the Earth. The way he does this is he uses a Laplacian sourcing function and expands it out into a series where he cuts it off based on the order of the frequency that appears in that expansion. These are the famous Laplace tidal equations. He's able to specify 4 species of tides, or the diurnal, semidiurnal, terdiurnal, and long period. These will be later categorized by Darwin and Dudson into the familiar M2, N2, S2 tidal naming convention that we know now, as well as the Dudson coefficients. So here they are. The one piece of math I have in this talk is the Laplace tidal equations. So for a fluid sheet of average thickness d, he assumes that there's no large variations from the height of the ocean, and he also assumes that there's no land anywhere. It's just an aquaplanet solution. The vertical tide elevation zeta, as well as the horizontal velocity components u and v in the latitude phi and lambda directions respectively, satisfy Laplace's equation here, where capital omega is the angular frequency of the planet's rotation, g is the planet's gravitational acceleration at the mean ocean surface, a is the planetary radius, it's again assumed a spherical Earth, and capital U is the external gravitational tidal forcing potential. So once you solve these out, using some approximations and some simplifications, you find 4 distinct species of tides. Moving forward past Laplace, we get to Kelvin and Darwin, who we're starting to get to the point now where continuous series are being able to be taken of the tides using recording devices. One such example, which is a pretty simplistic one, is that you just tie a marker to a buoy in a tube, and you have a rotating drum, and the pen traces the height of the tides over time on the rotating drum, and you're able to get a continuous series of the tides in that respect. And of course, over time, this is engineered better and better, and more accurate predictions are given. Using Fourier analysis and long records, the hope was that the tides could be decomposed into the various species, which were terdiurnal, semidiurnal, diurnal, and long period, which were predicted by Laplace. With so much data, rather than needing 18 and a half or so years, you only really need 1 year of records at this point, because that's enough time to pull them apart. And once this was achieved, Kelvin and Darwin were able to start to really list out the tidal components, and in fact, the naming conventions that they used still persist to this day. On the other side, rather than trying to record the tides, trying to predict the tides was making advancements too. One way of doing this was using tidal prediction machines, which are an amazing feat of engineering. What you do is you get a drum which rotates, but the pen, rather than being moved by the tides, is moved by a series of pulleys and gears, each rotating at the predicted magnitude and frequency of a tidal constituent. So this allows you to tune for a specific area once you've figured out what those constituents are and predict when the next high tides and low tides will be. The most intricate such machine was known as the India Office machine because it was used by the British East India Company. And it had, at first, 20 different components that it summed to create this prediction, and it was later upgraded to have 24, which is essentially all of the tidal constituents that matter at that point. So here we have the table of tidal constituents. This is more or less what Darwin produced. We have our semidiurnals, our diurnals, and our long terms, and what our compounds are our terdiurnal terms. So as you can see, there's four here that have a period of about half a day, which are M2, which is the dominant tide everywhere on Earth, except in very specific places where it's suppressed. S2, N2, and K2. Then as we go down, we have the diurnal ones. K1 and O1 are both important. K1 figures actually into the polar tide, which I'll talk about in a bit. And then the longer term ones. As we get to longer and longer terms, the magnitude of the tide on the Earth is smaller and smaller, so it matters less and less. But there's actually one more longer term one that's not in here, which is the solar annual tide. But I think at that point it's down near the millimeter scale, so it's not incredibly impactful. So at this point, most of what the theory has done on the real Earth is figured out a bunch of points of high and low tide along the coastlines. But what's not understood is how that progresses across the ocean. At this point, by the late 18th and early 19th centuries, we now have information on the other side of the Atlantic at a high degree of accuracy. So we kind of have these points, and a lot of attempts were done to just draw lines between points of high tide at various times past Greenwich Mean Time noon. But what this was lacking was a notion of amphidromic structure. So briefly put, amphidromic structure is this idea that you can get points of no tide where the tidal constituents add in such a way that there's no mean variation. What this is also equivalent to is the point where all the different phase lines of the tides meet at one point. So what you get is kind of a bullseye shape of tides moving around in a gyre. If you've heard of the Great Pacific Gyre where all the trash collects, this is an example of that, of a point where there's no tide and things are rotating around. Early cotidal maps don't have this. The other thing that's being developed at this time is, on the geophysical front, work is being done to understand the pole tide. Now, where the pole tide comes from is the fact that the pole actually wobbles a bit as it moves around the sun. And this creates a tide that rotates the pole. It's usually quite small, but there are some areas in the Barents Sea where it's actually one of the more dominant tidal constituents and affects how ships move. So that's actually still an open question, is exactly why the polar tide is important in the places where it is important. The other questions that are coming up are ones about how the dissipation of the tides affects the orbit of the moon. These questions will go on to be open questions until the advent of high-performance computing and satellite imagery, at which point attempts will finally be made to quantify the global dissipation of the oceans. Here's an example of an early cotidal map. This one is done by Edwin Houston in 1891. We can see that there's no points of zero tide. The lines are just drawn more or less straight across. The fact that there's bumps in it here is due to measurements taken at sea, where they found that the tides were not exactly straight lines. And what we do notice is that there's no information about the polar tide. These kind of, there be dragons. There's just no idea what's going on there. Same with the northern pole. And again, there's no points of zero tide, so there's no amphidromic structure. In a bit, I'll have a more updated one which shows that. So moving to the quite recent past, this year is actually the 100-year anniversary of the founding of the Liverpool Tidal Institute. The story of tidal measurements taken at Liverpool starts with a man named Jeremiah Horrocks. He lived from 1619 to 1641, so only about 22 years. He was one of the great scientists of the 17th century. He was a man even Isaac Newton held in high regard. And he's most famous for predicting the transit of Venus, but he also had a great interest in understanding the ocean tides, and in particular verifying that old claim that the moon was part of what caused the tides. The Liverpool Tidal Institute was founded by two people named Proudman and Dudson, and it actually in 1987 was renamed to the Proudman Oceanographic Laboratory. So Dudson comes up a lot because he's known for his coefficients. So he felt that the naming convention that had been dreamed up by Darwin was insufficient. It wasn't rigorous enough. So what he did is he created a system of angular coefficients. The Dudson numbers are a systematic way of labeling all of the harmonic components of the tides based on lunar time, longitude of the moon, longitude of the sun. So there's 6 frequencies that influence the tides, and so you can uniquely specify each tidal component by giving a list of 6 numbers. The Liverpool Tidal Institute, which is, I said, 100 years old this year, has been one of the premier locations for research into the oceans over the last century. The work done there has contributed to our understanding of worldwide tides and has especially contributed to the understanding and gathering of measurements of the ocean heights in the area directly surrounding the UK. So we are finally now at the present. So what has been happening recently with the oceans? Well, recently, going back about 30 years, the computer revolution was a huge boon to ocean tidal research, as it was to almost every other field of inquiry. The ability to use computers to address difficult questions has improved our understanding of the coupling between the tides and the atmosphere, as well as many other areas. It's also allowed us to investigate the normal modes and resonances of the real ocean, which is important because we don't live on an aquaplanet, like Laplace used in his approximations, and the fact that we have continents really does change the way that the tides progress across the oceans. With the advent of computers and satellite technology, we're able to finally address that question of the global dissipation, right? And global dissipation of the tides comes from 2 main sources, one of which is dissipation via internal tides, and the other is bottom layer drag. The way internal tides work is, imagine you have a tide passing over a smooth surface, and then there's a bump in it. So the tide's going to hit the bump and deflect upwards. And so as you have tides moving upwards through otherwise streamlines, you get turbulent flow, and that produces dissipation and energy loss. Bottom layer drag just has to do with the fact that water is a viscous medium, so it has energy loss as it passes over the bottom of the ocean. So these 2 effects have been quantified in a variety of ways in an attempt to understand how the orbit of the moon is slowing. The reason that this question actually came up was that once, here's an interesting corollary, was once they measured the global dissipation fairly accurately, they noticed that if you just said that that dissipation had been the same throughout history, then the moon ends up inside the Roche limit way too soon. The Roche limit is the orbital point at which any closer to the Earth, and the moon would fall to the Earth. So this raised the obvious question of how has dissipation of the oceans changed over time? And so what we found out from this was that dissipation must have been anomalously higher in the past, and this is the area that I work on a bit, is the glacial oceans. I'll get to that in a second, but I want to hint towards it. Satellite imagery has also allowed us to get increasingly accurate measurements of the height of the ocean, which has allowed much more detailed maps to be created of cotidal lines as well as elevations and amplitudes. One such example is the TOPEX Poseidon joint mission between the NASA and the French Space Agency. As you can see here, this is a combination where the color tells you how large of an amplitude tide it is, and the white lines mark lines of phase. So you see these points like in the Pacific, you see that big gyre in the middle, that's the Central Pacific Gyre, where the trash collects. We also see one in the Atlantic, and it's hard to see, but there's a lot of interesting stuff going on around the coast of the Great Britain. So this is much improved. This is actually the TPXO 0.5, which is the highest resolution one yet done. It has a resolution of, 7 kilometer intervals with an accuracy of 3 centimeters for height, and it ran for 5 years until a malfunction caused the mission to end. It was launched in 1992, and it helped revolutionize oceanography, there we go, by providing data previously impossible to obtain. It's quite hard to take measurements of how high the ocean is on a ship floating in said ocean. So now we get to talk a bit about what I've done over the last year or so, working on glacial oceans. What I work on specifically is investigating Heinrich events, which are rapid deglaciations of the Laurentide ice sheet during the last ice age. They occur over incredibly quick geological timescales, 500 years for much of the Hudson Strait and the Hudson Bay to vacate into the North Atlantic. And we don't quite understand, we don't have a working model of exactly why they occur with the periodicity that they do, which is about 7,000 to 10,000 years. Aside from that, a fair amount of work has been done on the glacial oceans. There's work by Peltier and Griffiths examining the polar tide at the last glacial maximum around Antarctica. And it's generally known that the height of the M2 tide was far greater in history, which is, we know that it had to be greater to create the amount of dissipation necessary to get the moon to where it is today in historical times. Specifically, we notice a much increased amplitude of the tides in the North Atlantic basin, which ties in with Heinrich events because you have right where the mouth of the Hudson Strait will eventually open up as the ice melts. You have some of the highest tides in the world, tides which are about 11 meters in height from the M2 alone, and when you add in the other constituents, you can get a local maximum of about 14 meters. So that's higher than the Bay of Fundy is today. Now, of course, since we're working in the past, we don't have observations until we can invent a time machine, so we have to do with computer modeling. So here's an example of a phase map produced by the solver that I used. As we can see, we have the Atlantic Gyre, the Pacific Gyre, and one thing we do note is that if you look around Antarctica, you see a continuous transformation of phase all the way around, which means that there's a tide moving around Antarctica, or the polar tide. Here we see an amplitude map. This is at last glacial maximum. You'll notice that the coast of North America is largely covered with ice, including Newfoundland. And you'll see that we have incredibly high tides right where the Hudson Strait is going to open up. This horseshoe-shaped area of high tide is because the North Atlantic basin, when ice is covering both sides of it, is very near to resonance. So you get a much higher tide there than you would otherwise. As the Laurentide ice sheet deglaciates, one interesting fact is that the high tide actually tracks backwards with the retreating ice sheet. So it consistently pounds it back as it moves up, which is one possibility for what causes Heinrich events to happen so quickly. Another area of present research is investigating the ocean bathymetry. Using signals that are able to penetrate water but not ground, we've been able to map the subsurface bathymetry of the ocean. And it's a far cry from Laplace's uniform depth. There's much variation over the course of it. One such mission was the Earth topographical one, where the one here refers to the 1 arc second of resolution. The previous missions were the ETOP-02 and the ETOP-05, which respectively had 2 and 5 arc seconds. As ocean depth is an important factor with how the tidal constituents and the oceans behave, understanding it allows us to model things much better. Coupling this with missions that investigate a single water column in great depth, we can build ever more accurate ideas as to how the oceans realistically behave. Another present addition is high-performance computing. High-performance computing involves a large number of computer cores to efficiently split up a task. Now, one of the things that this requires is playing around with the code to make it actually work, but it's incredibly powerful. You're able to do full global simulations of the oceans at high levels of accuracy in reasonable amounts of time, which has opened up the horizons we have for creating more and more complex models that have more tidal constituents, better internal tidal models, higher resolution bathymetries, and other inputs such as surface temperature, wind speeds, to get more and more accurate. I've actually used this here at U of T, where we have a cluster called Niagara. It's one of the largest in Canada. And I used it to create those, to compute the data I used to create those images of the phase and the amplitude of the glacial ocean. So, the future, where is ocean science going today? Well, climate change is one of the biggest issues we face right now. And by better understanding the ocean and how it plays in with other inputs to the climate, we can better determine how rising waters will affect communities across the earth, specifically in places like Bangladesh, which has very low lying lands and floodplains, as well as the Netherlands, which is, I think, 95% below sea level, something like that. So understanding how the climate will affect these places is important on both a scientific and a humanitarian front. The area of coupled climate-ocean models is being very intensely researched right now, with much effort being put towards more and more accurate models that have more and more inputs from different areas. One example of this is the Community Earth System Model, or CESM, which began actually without any coupling to the ocean or sea ice over 40 years ago, but since then has progressively been updated to include these inputs and their interaction with other effects. Given that climate change is right around the corner, it's kind of imperative that we get a handle on how these things work together to create better models. So here's an example of all the different things that go into a climate model. Ocean bottom topography, which I've talked about, vertical overturning, ocean currents, air changes, the hydrological cycle, sea ice. All of these things have physical models associated with them, which take in as inputs a few of the others. So trying to create an accurate model is a highly nonlinear question, which takes vast amounts of computing resources, which is why high-performance computing, where it is now and where it will be in time, is so important. Understanding the interaction of these pieces also brings us closer to predicting long-term weather patterns, and also just getting better at predicting the weather in things like hurricanes, which, if you've been following, have become more and more devastating to the coast of the United States over time. Another area of research that understanding the oceans plays into is ocean acidification. So for the more ecological people in the room who know about this, ocean acidification is a decrease in the pH of the oceans. This interacts strongly with ocean chemistry and is devastating certain biomes like the Great Barrier Reef. Another example of this, not acidification, but was the spread of nuclear contaminants after the earthquake that struck Japan and broke the Fukushima reactor. Knowing where those isotopes end up and where that pollution ends up is important for conservation and cleanup efforts. Same thing when oil spills like Exxon Valdez almost 30 years ago now, as well as the New Horizons. If we know how the ocean is going to move pollutants around, we can better and more effectively contain them. And so ocean circulation is still an area of research, given that it's driven by heat cycles, wind cycles, larger scale things like overturning circulation. So we need to do more investigation on that, and that's another future area. Another one is the impact of melting ice on the oceans. So we know that melting ice can have drastic impacts on the ocean and climate due to something called the Meltwater Pulse 1A at the end of the Laurentide deglaciation. It increased sea levels by 100 meters, which is huge. And although this is on the extreme end of events, deglaciations that could be possible with the Greenland as well as the Antarctic ice sheets could have similar, if not as large, effects. When fresh water is poured into the ocean, it disrupts certain currents. So one example is that when all the water fled off of the Laurentide ice sheet into the North Atlantic, it depressed something called the meridional overturning circulation, which is the main current that pulls water from the poles into the center of the Atlantic and creates a heat exchange across the northern and southern hemispheres. When this shuts down, you don't get convection of heat, and the global temperature drops a number of degrees, which, I mean, might help address climate change, but not really in the way we want it to. The other thing is that when fresh water enters into the ocean, you can get a salinity gradient, which can cause dual diffusion, where the cold water has less salt, so you get currents moving in direction as the cold water wants to sink, but the salt wants to diffuse into the fresh water. Understanding, again, the circulation of the tides helps us know where icebergs are going to end up closing or opening various shipping lanes. That's actually one of the interesting things with climate change, is that the Northwest Passage became a reality when we thawed enough ice in the Arctic. And the other thing is that as ice melts, certain coasts become exposed, and this can change the global dissipation, which will affect the height of the tides over the millennia or larger than millennia timescales. And another interesting piece about understanding oceans is that we're not the only planet that has oceans. We know that places like Europa and Enceladus have oceans as well, and they're of great interest. There's a mission that's going in 2022 called JUICE, or the Jupiter Icy Moon Explorer, which will be flying to Ganymede and will include 2 flybys of Europa. Enceladus is actually one of the most interesting ones because it's likely to have a 30-kilometer deep ocean. For reference, the ocean depths here range, I think, from 11 kilometers at Challenger's Deep up to surface level. So 30 kilometers is a lot of ocean. And it's buried under a cap of 30 to 40 kilometers of ice. The way this was determined was actually by watching it orbit Saturn and watching its crust deform away from where its center of mass was as it compressed the fluid around. Now these are extreme cases, but one of the things is that with our tidal models, we have an n=1 case. We have the Earth. So as we get more places to test this stuff, we can improve these models and get general understanding of how tides operate in other systems, which far in the future might be useful for terraforming efforts. Understanding the oceans, again, ties back into the first point I made, that it's where life develops, and it's where life could have developed in other places. So understanding the oceans can help us answer questions that have, played with humanity for a very long time. And that's my talk, so thank you. Do we have any questions? Yes, Shane.
More about the 40-kilometer deep ocean. Sorry, how did they figure out
So
30
so this is
meters of ice and then 40 kilometers deep?
it's really cool. You use you watch it as it passes around Jupiter, Saturn, and you also watch it as it interacts with other moons like Titan. And what you can show is that the surface of the planet is moving relative to the center of mass of the planet. So the way we get a bound is by saying, imagine you have like a water balloon around a core, right? As the water balloon moves, the core will hit the edge of the water. So we can guess what that distance is by how far apart the surface moves relative to its center of mass.
And that helps you to estimate this
That
thickness
of the ocean,
crust as well.
the way to, yeah, and the thickness of the crust as well. So you can get those two numbers by playing with gravity and observation.
Fascinating. Thank you.
Yes?
Is anybody doing any predictions about how fast the ocean level is going to rise?
I'm sure people are. I don't know any off the top of my head who are doing that here at U of T, but I know that it depends heavily on how quickly the temperatures are going to raise, and also on the models of how the ice caps are going to respond to this. So it's kind of one of those questions that we have fairly large error bars. I've heard somewhere between 2 to 5 meters in the next 100 years, and that's quite a lot. If it's on the upper end of that, you're going to see it's not really the loss of land that is the problem, and people get this wrong in the popular media all the time. It's the human element. If you flood Bangladesh, you suddenly have 300 million people with nowhere to live who are not likely to be taken in by India or China. So you have humanitarian issues that need to be developed. The other angle is that a lot of the places where we have bread baskets, where we produce our food, are low-lying floodplains. So if you have a rise of a few meters, then you suddenly lose a lot of the farmland on the Nile River Delta, on the Amazon River Delta, and on the low-lying rice paddies in China, which produce a lot of the food that people survive off of. So it's not just the environment, it's what the environment does to our ability to have supply chains that are the kind of large problems. Yes?
Could you give a loose explanation as to why tidal dissipation affects the moon?
Yeah. So you have a system where the moon is, you can think of the moon as pulling the tide away from the Earth, and as they move around like this, you get that's the diurnal component. As the tides dissipate into heat, that energy has to come from somewhere. And where it comes from is the angular momentum of the moon. So as the moon slows its rotation down or speeds it up, in either way, it moves further or closer away to the Earth to keep the, it's just conservation of energy is where it comes from. Yes?
How does the Argo's network of buoys help you in understanding your tidal wave dynamics?
Like in my work particularly? Or?
What you're presenting.
Oh, in general. Well, that plays into the notion of measuring water columns in a specific place, right? So there's only so much we can do with satellite imagery, but having buoys in the ocean themselves provides that information of specific places moving up and down, the motions at certain places. So it kind of supplements it on the surface level. But. Okay, well, if there's no other questions, thank you.